Hello everyone, we are almost towards the end of our sensor parameters. So, we already have discussed excitation in our last lecture. What is excitation? And we said that excitation is something which is kind of act as a bias or an external energy that we give to one sensor in order to operate the sensor. And then we discussed the dynamic characteristics of a sensor, which is again very important. And we have seen that how dynamic characteristics of a sensor can be useful and how we can make use of the dynamic characteristics and what are the different conditions where dynamic characteristics can be utilized, or we should take care of dynamic characteristics. So, we already have seen those aspects. Today, we will discuss one very important parameter, which is response and recovery time. Now, before we start response and recovery time, let us first define what is a response of a sensor. So, as far as the response is concerned, to make this discussion much easier, what I have done is I have shown a plot where this blue line shows the response of the sensor. Response of the sensor means how sensor responds with respect to inputs. This is one sort of response that we generally record for a sensor. What I mean by that is, for example, in case of temperature sensor, you will find we record the response of the sensor with respect to temperature. Then there is another type of response which is known as temporal response. Temporal response meaning when you record the response of a sensor with respect to time. So, when a sensor is detecting a certain sort of output or a certain sort of kind of parameter, how the sensor behaves with respect to time is known as temporal response of that particular sensor. Now, response and recovery time is related to the temporal response of a sensor. So, from the name itself, it is very clear. The time a sensor takes to respond to a stimuli is known as response time. And what we have defined is the sensor or the time taken by a sensor to reach to the 90% of the maximum value. This is the maximum value of the sensor response. So, again this is a temporal response, this x axis is time, and then you have say response in the y axis. Now, this particular value is the say maximum response. You can say this as S maximum. So, it is like maximum response, and this point is showing 90% of SM, that is 0.9 SM. So, the time taken by the sensor to reach to this maximum 90% of the maximum value is known as response time. So, if your response time is higher, the sensor is performing slower. So, ideally what we need is a very small response time, so that we can detect a certain output or a certain stimuli in a very short duration. Then similarly, once the response reaches to its maximum value, it kind of saturates, and then when you remove the stimuli, so this is the point where you have taken your stimuli out. Again, we will take an example of temperature sensor for the sake of simplicity. Say this is a temperature sensor response, wherein you have applied say 50 degree centigrade to a temperature sensor. So, this is the temperature sensor, and you have started recording the response of this temperature sensor with respect to time. You have seen that with time the sensor response is increasing, because your temperature is now 50 degree, which is higher than room temperature. It was, for example, say it was kept in room temperature. Now, because the room 50 degrees is higher than room temperature, the response of the sensor is increasing with respect to time, and then it reaches to its maximum value. Because your applied temperature is constant 50 degree centigrade, that is why your response also will to some extent saturate. And at this point, what you have done is you have taken the source of temperature away, or you have bring that sensor back to room temperature. In that case, the response of the sensor will start decreasing with respect to time, that is shown over here. So, this line shows at the moment you have taken your stimuli away from the sensor, or the moment you have turned off your stimuli, right. So, the time the sensor takes to come back to the 10% of its maximum value is known as, so this is the time, this is known as recovery time. So, the response time is the time the sensor takes to reach to the 90% of the maximum value, and the recovery time is the time sensor takes to reach to the 10% of its maximum value when the stimuli is removed. That is known as recovery time. Again, for a sensor, it is desirable that you have a very short recovery time. If you take an example of say a digital thermometer, you need to use that digital thermometer multiple times for multiple patients, or multiple times to a same patient as well. So, in that case, when you put the thermometer, digital thermometer, ideally it should provide you a output or the body temperature value as soon as possible. So, the response time should be smaller. Similarly, the moment you take the sensor out, the sensor again should go back to its initial position, so that you can reuse the digital thermometer again as soon as possible. So, ideally the target, until and unless your application is demanding otherwise, the target is to keep response time and recovery time as short as possible. In that case, your sensor will perform faster. You can say that my sensor is responding faster. Okay. So, this is all about response and recovery time associated with a sensor. Then there is another very important parameter which is known as drift. So, drift is a parameter which actually defines how your sensor response is changing again with respect to time. Okay. So, to again make the discussion clearer, I have shown a plot over here. For example, say you take again an example of temperature sensor. You have a temperature sensor, you have kept this temperature sensor at 50 degree centigrade, and ideally you should get a response similar to this straight line. So, it should be constant with respect to time as long as you are applying 50 degree centigrade. But in practice, you may find that with respect to time or after a certain duration, your sensor response is decaying or decreasing. Okay. The extent of decrease may vary, but it is decreasing. Say till say 2 hours, the sensor response was more or less constant. After 2 hours, the response started decreasing. Then this decrease or the difference is known as drift. So, from the discussion itself, it is very clear drift is not something which is desirable. However, based on the material used or material degradation, electrode degradation, or because of some external parameters as well or external influences as well, you may find that your response of the sensor is decreasing or changing with respect to time. That means your sensor is having a drift. This timeline may vary. This is just a kind of representation. I have given you an example. This can be 2 hours, this can be 2 days, this can be even higher, or at times this can be even as short as say 2 minutes. In that case, your sensor has high drift. So one has to avoid that drift in order to work with the sensor. In practice, you may find many sensors are suffering from drift, or when you develop a sensor, fabricate a sensor, you may find that drift is there. Now the question is whether you can work with a sensor which is having a drift. So again, it's not a straightforward answer. It depends on the kind of application you are targeting. In generally saying, I mean, it's an in general comment that I am making is you can work with a sensor that has a drift, but then you have to work with the system. There are ways where you can work with a sensor that is having a drift. Again, drift can be very random, drift can be predictable. So if it's a random drift, it's very difficult to work with. If it's a predictable drift, then you can work with that sensor. Okay. So again, in generally speaking, drift is not something which is desirable, but that again doesn't mean that a sensor having drift can't be used at all. It depends on the application again. Then there is another type of classification. I have listed it out over here. So a sensor can be active, a sensor can be passive. So an active sensor requires an external power for operation. One example can be thermistor. So if you are working with a thermistor, you definitely need a power source in order to operate that thermistor in a particular temperature range. But there are sensors which generates power, that generate power. For example, if you take example of photodiode, you will find that they actually generate power. There are piezoelectric sensor where if you apply pressure, they generate power. In that case, you may use those sensors without taking or without using any external power, and those sensors are known as passive sensors. But you will find in many cases these sensors are also used with external power. So this is a separate discussion altogether, but as far as the classification is concerned, active sensors, for example thermistors, strain gauge, all these things require external power for operation. But if you have photodiode, piezoelectric sensor, they can be used without an external power. That is the point of discussion. That is what I mean to say. But it doesn't mean that photodiode cannot be used with external power. There are systems where we use external power and then also use photodiode, or to operate the photodiode we also take help of external power. Okay, just be very clear about that. But based on the power generation or the requirement of external power, we classified sensors in active and passive. Then we have absolute and relative sensor. Now in case of absolute sensor, the reference of the sensor is fixed. For example, if you take a thermistor, for thermistor the reference is fixed. What I mean by that is, for example, if you procure a thermistor, you know what will be the response at 50 degrees centigrade. So the reference is fixed. That is an absolute sensor. But in case of relative sensor, they work based on the measurement or comparison. There is no fixed reference. For example, thermocouple. Thermocouple works based on the difference of temperature. If you increase the temperature from say 10 degree to 20 degree, 10 degree centigrade to 20 degree centigrade, you will get response R. If you increase it from 30 degree to 40 degree, you may get a similar response. So it's like you need to compare. It depends on the delta T, because in both the cases the difference of temperature is, or delta T is 10 degrees centigrade, right? So in those cases we call it a relative sensor where no fixed reference is there. Okay, so that is how we classify absolute sensor and relative sensor. Then there is another term which is input and output impedance. So input and output impedance is a kind of circuit consideration. One should know the input or output impedance of a sensor in order to design the interfacing circuit, because if the output impedance of the sensor is not matching with an input impedance of an interfacing circuit, it may create an issue. At the same time, you also should know what should be your output impedance of a sensor. To give you an example, here we have taken a sensor which generates voltage, and here a sensor that generates current. That means the output of this sensor is voltage, the output of this sensor is current. Now, for a voltage generating sensor or a sensor which provides output in terms of voltage, we connect Z out and Z in series. Secondly, the Z out in this case should be low, because if the Z out is very high, most of the voltage will again drop in the sensor itself. Here you won't find the output from the sensor. So it's better if you use a low Z out for a voltage generating sensor. However, in case of current generating sensor, first your Z out and Z in should be in parallel, and then the value of Z out should be low, because if your Z out the value of Z out should be high. In this case it should be low. In case of current generating, it should be high. The value of Z out in this case, if you keep the Z out low enough, then what will happen? The current that is generated from the sensor will shunt through the Z out. So most of the current will pass through the sensor output impedance. Then you will not get much of the output in the interfacing circuit, which is not desirable. So if you keep your Z out high, most of the current will pass through Z in of the interface circuit. That is the idea. So it's not very complicated. The idea is to transfer most of the output to your interfacing circuit. For voltage, I repeat, for voltage generating sensors, your Z out should be low. At the same time, you keep your Z in high, so that most of the voltage is getting dropped in Z in. Similarly, in case of your current generating sensor, you keep your Z out high and your Z in low. If you keep your Z out low in this case, then most of the current will pass through it, which is not desirable. So you keep your Z out as high as possible. This is regarding input and output impedance of a sensor. So this part is more or less associated with the interface circuit. Okay.
So we are almost at the end of our discussion related to sensor parameters. So we already have seen that there are various parameters associated with a single sensor, and each of these parameters are important. In many cases, it's very important you look after all these parameters, but you'll find that few of the parameters that we have discussed are really of higher significance. So in that case, you have to have extra care about those parameters. And today also we have discussed one very important parameter, which is response and recovery time. And we already have briefly discussed that response and recovery time is something which will decide how fast your sensor responds, right? So just to give you an idea, related to this response and recovery time, what I would like to mention is, you may find temperature sensors. uh, why I'm taking this example, because I probably have said before also that temperature sensor is something which you can relate to very easily. So you may find different temperature sensor, or you may make a sensor to detect temperature, where the response time is probably fine, but the sensor recovers very slowly. Okay, at times it may take, you know, few 10 minutes, maybe say 20 to 30 minutes just to recover. So in that case, one has to work with the sensor so that you can reduce the recovery time, and then only the applicability of this sensor increases. If you are making a sensor where the sensor itself is recovering, you know after a long time, you can't reuse that sensor for the next application. But there are applications where probably long recovery time is also fine. Just to give you an example, if you take a furnace, say a vacuum furnace you have, and then you increase the temperature of that vacuum furnace to say 120 degrees centigrade, and after the process is done, you have switched off the vacuum furnace. And usually when you switch off the vacuum furnace, you don't use it again, uh, maybe for next 1 hour, 1.5 hour. Or even if you use, even if it is not recovered, if the sensor is not recovered 100%, the sensor will again start rising from there and will reach again to this new value. If it is next time, if somebody is using for say 125 degree centigrade, then you may find it is again going back to the 125 degree centigrade. Doesn't matter whether it is recovered or not, it is no longer needed, because in the next application again you are rising the temperature beyond 120 degree centigrade. Or sometimes you can also rise the temperature to say 80 degree centigrade, but it recovered up to say, here where the temperature value is around, say 95 degree centigrade. In that case, even if you are using that sensor for 80 degree centigrade, you can set that temperature to 80 degree centigrade, and then slowly it will come back and settle at 85 degree centigrade. Even if it is not recovering completely to the room temperature, that is fine. So that is how uh, you can design the sensor for various applications. But if your application is, say, body temperature measurement or something like that, because usually in case of furnace you can wait for hours or half an hour, because it's an process where usually, that process takes time. If you want to heat something, you want to heat it for an hour, 1 hour and 1 hour 30 minutes, and there you can wait, and the recovery actually doesn't matter much. But if you are involved in an application where the recovery is absolutely necessary, for example body temperature measurement, you have maybe 100 of patients in front of you, and for all of them you need to check the body temperature. You can't wait say 20-30 minutes uh, before you check the next patient, then it will be a chaos. So in that case you have to decide, or you have to take a sensor where the recovery time is less. So the purpose of this discussion is to give you an understanding that when something is bad, it's not like it's bad for all the applications. In certain cases, you can compromise. You can actually decide to use a sensor with higher recovery, and then can put that particular sensor for that particular application, and things will be okay or fine. But if it is for some other application, where the recovery is absolutely necessary, or less recovery time is necessary, then you can't use that sensor. You have to choose some other sensor, or you have to design the temperature sensor where the recovery time is less. So that is how one can actually decide those parameters, and also can modify the sensor geometry or sensor active material in order to design their sensors. So these parameters are important. At the same time, one has to understand that what is good and what is bad. It's not like absolute, it's relative, and it depends on the application. So that is why I'm concluding the sensor parameter discussion with a note that good and bad will be relative to the application targeted. For certain application, you can actually have a sensor where some parameters are not that good, because again, cost is associated with it. So if you want to make an high specification sensor, then you have to pay more. But if you can do that same job with a low cost sensor, then why to go for a high specification sensor in the first place? So one has to be very clear about the requirement, and he or she should decide upon those parameters based on the requirement and the application. Okay.
So there are three take home messages from this lecture. First one is combined effect, that is sensor and system of dynamic characteristics may influence the performance, that we already have seen. The combined effect may influence the dynamic characteristics of the system. Response and recovery times are not interlinked. So what I mean by this statement is, in a particular sensor you may find that the response time is very high, but your recovery time is small. So they are not interlinked. A small response time does not ensure a small recovery time. So if you look at the sensor, a sensor response can be like this, where your response time is small, but say your recovery time is quite high. And at the same time, you may find sensors where response time is high, recovery time is low, or both are high, both are low. All these combinations are possible and they are not interlinked. The third thing that one should know is drift in a sensor cause low performance, which is again very obvious. I already have discussed that if there is a drift, then obviously the performance of the sensor will not be as good as a no drift sensor, because your response itself is not stable with respect to time. Okay, so drift in a sensor is not desirable. And what are the reason behind the drift? The reason could be degradation in the material, active material, degradation in electrodes. There might be a problem with excitation as well. It's not something which is very specific to sensor. In system level also you may find there is some issues which can lead to a drift, but for the time being let us consider the sensor consideration only. Then the drift can also be because of some external factors. External factor is in, if you are making a temperature sensor and your sensor active material is exposed to the environment, then humidity may influence the material. You may find at high or in a very humid condition your sensor is showing drift. That means the humidity is influencing your active material. Okay, so there might be different other reasons which can lead to a drift, and the drift is not desirable. Now I have a question, which is there a way to address the drift issue without changing the sensor? The question is, for example, say you have a temperature sensor which is showing some sort of drift with respect to time. So can we address this drift issue without changing the sensor? So we want to use the same sensor, and then at the same time we want to get rid of the drift, or we want to work around the drift. Is it possible? Let's think. To some extent probably I have answered during this lecture, but I leave it to you to think whether it is possible or not. So in the upcoming discussion we will start sensor physics. We are more or less done with sensor parameters. We have seen lot of parameters associated with sensor, but there are few more parameters as well which I may discuss while I am discussing sensor physics, but most of the important parameters are already discussed, and we also have seen what are the significance associated with those parameters. In the coming lecture, we will start with sensor physics. Thank you.